to protein. However, the energy is quite different, and the methods for structure prediction are quite different than in the case of proteins. In talk, I'll start with an outline where by background information, I was interested in. I'm going to focus on the sum protein to determine the scaffold with structure. These secondary structure prediction in RNA is much more important than the second, because to our extent the secondary structure of hydrogen forms scaffold of the 3D structure. Wang Landau algorithm that we speak of concerns Carlo, specifically in the Boltzmann and Monte Carlo sense. I need to give background on the Monte Carlo algorithm by the statistics community in the recent past methods, and that gives the proper background for understanding how to implement the Wang Landau algorithm, which we do in the secondary structure. We apply to compute the so-called density of states. This means that if you were to enter the minimum energy to highest energy and discretize this instance, we want to know the number of structures lying each in. That is called density of states. Wang Landau gives a version to this density state from which we can later compute the partition and key thermodynamic parameters. The state of art means of computing the secondary structure includes an exhaustive algorithm, Ivo Hoffer, Vuchti, group, and an uncommon option or sub-off algorithm. Again, this has to be numerous, so Wang Landau gives a very comparison to this. We then implement Wang Landau for hybrid of two RNA sequences. We describe partition function, and again, from the partition function, you can compute thermodynamic parameters, including them. And this is a way to calibrate an experimental protocols for determining the melting hybrid RNA sequence. We'll finish by giving an overview of current and future work. Background. RNA is a critical molecule which is the reason for a number of prizes both in chemistry and physiology. The most recent with Blackburn of polymer and the role. However, these other novel properties of RNA, including its catalysis, which is short for, we'll talk also about switches, the bacteria, which undergo a conformational change, turning the other form of gene by microRNA. RNAs of entry is thought played the starting role in primordial soup, where RNA can fill two roles. There is still HIV, C in RNA genome, and forming a role is most important biological reaction. This is a peptidyltransferase reaction on the ribosome and amino acid growing peptide chain, which is RNA. So RNA has very many roles, perhaps least that's been understood is its effect on material modeling, which is perhaps the most important way of using gene regulation. As markers RNAs been found important messenger RNA, more reliable messenger RNA. I think his lectures in biology, although I did want to study that microRNA play an important role in gene good deal of research in the targets of microRNA are predicted by software that depends on hybridization energy of the microRNA to get the target messenger RNA. For instance, a paper of the lab methods dynamic model. Now, moving on definitions before to talk about Monte Carlo algorithms. The secondary structure is a kind of planar graph. It is an aggregate on the free of the circle and a base pair between Watson and Crick, located by arc of the circle. Requirement no crossed arcs. The crossed arc is called the exists in tertiary structure, but the secondary structure consists of pseudons. This is for technical reasons to allow time dynamic programming algorithm for partition and for the free energy structure prediction, where it's yielding an AP problem. The figure on the left just present secondary structures. And in the case of our strain, forming for a three-dimensional structure. Example 2, taken from pseudobase of YRNA, which plays a role in full incorrect RNA, involves the arc. You see a typical type H pseudonym. We work with a thermodynamic model, standing energy model, at a level. The further prediction for RNA secondary structure was over by assumed a minus 1 energy for each base pair. Very naive, the state-of-art energy model depends on measured parameters from UV absorbance, also called optical melting. The idea is that free energy is due to stack base pairs, not the existence of these stack base measurements are in the photometer, where the idea that if you have a RNA solution, then that single-stranded nucleotide plate, which will more easy on. So the absorbance at 280 primary absorbance for cytosine single-stranded region, whereas double-stranded regions are protected. In addition to base stacking free energies, Turner measured loop entropy, and this depends on classification of different kinds, including a multi-loop. Those then can be a helix, consists of stack, hairpin loop, a bulge, an interior loop, and a multi-branch for which one applies an energy value and on the number junction multi. So algorithms, thermodynamics based approaches for secondary structure, and for stacked base pairs, as well as different groups. This is an example from Info where the terminal base pair is the GC for each one of 6 possible choices of base pairs. U, A, G, C, GU, and UG. There are different measures of free value base stack. So, overview then of RNA structure and thermodynamics. The current methods start with a metropolis algorithm that was then extended to allow for reversal Markov chain, and would like to give a brief overview up to Wang Landau meeting under the novel Landau algorithm. The problem is a kind of random walk of pain. In our situation, our secondary structure from secondary structure to another, either add or remove a single base pair, the transition x the minimum of 1 and for the number of state x times the probability of the new state divided by the Boltzmann probability. And we will show that in certain conditions, the stationary distribution of the Markov chain is a condition such that the state x is equal to e to the minus energy effect of RT divided by the partition, which is the sum of all such Boltzmann factors. In both protein and RNA is that we find irreducible aperiodic chain as a partition. This is a classic result from math. If you'd like a self-contained new proof, you can take a look at an appendix of the book that both where in one of the chapters I developed a new proof of very and we're relying on any external results from statistics. Detailed balance is a definition physicists use for a reverse marching, which satisfies the requirement that for any x, the Boltzmann probability, the stationary probability of transitional probability of x to y is the stationary probability of y to x. Then one showed that the Boltzmann distribution is the stationary distribution, and it's known the Boltzmann distribution concentrates on the lowest energy states. Detailed balance does not hold for our structure. So we can start off with the empty structure. The nearest neighbor forming a hairpin. The first the energies of those and do the computation of the partition function. Simply. So for this reason, Hastings introduced a small change, the transition which renders the underlying Markov chain reversible, and the difference is probably going from x to y, 1 and e to the minus delta e over p times 1 over the number of neighbors of x, that's what we had before, times numbers of y. This term, if you do a small calculation, easily shows that the underlying Markov chain is reversible, and hence we have a converged distribution. This is right to the well-Metropolis Hastings algorithm together with simulated link. If you get the statement 7 through 10 step, if the energy of y is less than the energy of x, or y is random goes in median of x, then we update x to y. Otherwise, we perform the loop, which ensures that we take an energetic unfavorable y of x if the Boltzmann divided by Boltzmann of x is greater than a randomly chosen z of 0. Monte Carlo is used RNA for kinetics of linear. Three different approaches: kinetic literature, various web servers. For doing kinetics of RNA, one in fact needs to pass from a time-driven Monte Carlo algorithm to an event-driven Monte Carlo. That's Gillespie's algorithm used on kinetics. Replicate exchange involves Monte has a ladder different where independent runs of Monte Carlo are taking place, and the different temperatures are swapped according to the probability of swapping replicate y at is minimum of 1, and e to the multiple of 1 divided by e to the minus delta over 2. So simulated tempering is a different approach rather than a ladder of separate Monte Carlo algorithms with each temperature probability to be full condition. Finally, moving on to Wang Landau. If the code conception of Wang Landau began originally with Wang and Landau's the ISCB model. There was an interest in applications and then where they used in order to do transcription factor like weight, and they did use X-ray structures. The alpha helix, they replaced the amino acid, use molecular dynamics together with Wang. There have been applications of Wang Landau as well in estimation of flow particle interfacing and graphene. Unlike we've spoken of so far, Wang is a random walk on the energy landscape as opposed to the underlying state model. If we are currently in state X, Y, which is the immediate successor, so a secondary structure by here, we take the new secondary structure Y. If we take that with probability, which is the minimum of 1, and of the energy band of X divided by the energy band of Y. That means in X, we prefer which are not visited as much as the energy band of state X. So the patient inversely proportional to the times that we have actually visited the energy of that state. And for the states is the non-state whose energy is a fixed discretized energy band. The Wang Landau algorithm is used to compute states. In fact, we need the density of states for it to be computed. The solution is to use in order to collect information on sample states, and the approximate density will be the approximate time current sample structure. We initialize this by starting each energy interval, setting the density of to be 1, the histogram of visitation to be 0. The original paper was set to be equal to Euler. At Monte Carlo step, we choose IX. We choose a random number 0. If the number is G of EX, the density of energy band of X, the old state, divided by density of states of the energy band of the new state, make a change. X is equal to the new updated Y. We at that point take the density states and the histogram, regardless of whether we effected an update of X. The modification factor is changed when the histogram is approximately flat. Approximately flat means that the average of all bins of the histogram differs from any individual histogram bin value most 3%. What happens that is a user tunable parameter. At that point, we define the modifications factor to be the square root previous. So if we were to square root of E, square root, etc., we want. Advantages of Wang Landau. Like other Monte Carlo algorithms, we can actually sample effectively stay in phase transition close to the critical period. I heard from a paper of Jerome Valspiel and myself a couple of years ago, where on the x-axis we have Celsius temperature from 0 to 1. On the y-axis we have the percentage base pairs. In this developing algorithm for each day, the partition function over all secondary structures having exact. You see this model position where temperature at which 50% of it and 50% are in the original fold, somewhere close to 90, 95 degrees Celsius. You see a curve which corresponds to the same computation that the Newton where -1 is per base pair. This indicates that Turner energy model actually used in this state-of-the-art for all thermodynamics-based computation allows for cooperative folding, whereas the new does not. So here, the pseudocode simply builds into the features of Monte Carlo discussed, the visualization of the modification of the histogram of the states, the update choice, their X is change Y depending on the random number of G of X divided by G of G and Y. The output of the Wang Landau algorithm on RNA is a relative density of state. We actually need the absolute density of state because we want to compute the partition function. In the case of RNA, even pseudo is possible. There's a cubic time algorithm, a variant to know for the number of secondary structures or the number of hybrids of secondary structures. So if you're simply interested in the number of structures, it's straightforward program. From that, if you multiply the relative density of states, the absolute density of states, and you compute the absolute function, the function, which is the sum of overall energy bands, the density of states at energy E times Boltz's factor in E. That we can obtain thermodynamic energy and especially the heat capacity. Heat give us further. Running with the next slide to small variant of the Landau algorithm. The program we have for in the process of building a web server is put Wang Landau for RNA, where you can see on the left-hand side the energy. The column is the density of states. The relative density are the lowest energy found in that energy during the sampling. So this is a small stable switch. Structural diversity, according to Higgs, is much higher for sampling. This is to be expected. Wang Landau is much better RNA swap in computing intensity of states. So that's Wang Landau currently the method for density of states. And at this point, I'd like to thank you for your attention. And we are playing at the closing session. We play in Berlin. A couple of you home here are playing this Tuesday.
Hello. I have a question. Did you Wang Landau whether Monte Carlo sampling working on ensemble and compare that with the other MMs such as
No, because it does something different. It's not computer function. We're interested in partition function because from that we can get the melting temperature. There was a recent paper indicating that by taking into account complicated existent days that are not accounted for by dynamic programming, the actual melting temperature is closer to the exterior. So traditional not really ideal for partition functions.
So is this a partition function computed using dynamic programming?
The whole goal of this research is that by finding the we can account pseudo-knots crisscross, all of which lead to NP-hard problems. So that's the whole of this research.
Okay, thank you.
All this admirable effort in order to improve the algorithms, comment about, where is the trade in problems with the algorithms, the problem with the energy function? Because, if the algorithm is not going to buy you much.
In all the does make a difference. There was a bioinformatics last year. Was the first author, and what they did was allow so-called zigzags of a particular form taken account for by RNA cofold or by Zucker algorithm unifold, and the predicted melting temperatures are much closer to thermally measured melting temperatures. So our hope is that by doing this, we can even closer to measured melting temperatures, and in this case, it would be a proven algorithm. Your point is very valid. It also depends on the but I think that we have somebody with the algorithm to make it here.
Last question. How big a structure is called to compute?
This is called. So we've looked at things like 70 nucleotides, 100 nucleotides. Much that is very difficult.